Hi, let's go over lab 1. So in lab 1, you're going to look at some oscillating springs. In a video in Pivot Interactives, you're going to place a mass on a spring, and you're going to look at different springs of different stiffnesses, K. Then you're going to set the mass in the video into oscillation, and you're going to measure the period of oscillation, the time it takes for it to make one complete up and down motion. Let's look at the formula for that period. The formula for the period, T, is equal to 2 pi times the square root of the mass that's on there in kilograms divided by the stiffness of the spring in newtons per meter. Remember that a newton is a kilogram times a meter per second squared. A spring constant is a newton divided by a kilogram. So if you take a kilogram divided by a meter per second squared, and you divide it by, and you put it in this formula, you're going to end up with seconds. All right, so if I were to graph period on the y-axis, t, and k on the x-axis, what I would get is an inverse function. Would look something like this. To verify that that's an inverse function, what I would want to do is to linearize it. I would want to try to somehow take the variables in that function and make it fit, force it to fit a y equals mx function, where m is a slope, a constant slope. So if I take that function and I straighten it out, so right now it's a square root function. If I get rid of the square, what I would need to do is to square that square root. So if I square both sides, I would get t squared on the left side. I would get 2 squared and pi squared. And when I square the square root, that goes away. So all that's left is m over k. So what I would get would be t squared equals 4 pi squared m all over k. So let me pull out that 1 over k and pull it to the side. Because the k is one of those things, I'm picking springs of different spring constants. So that's one of my variables. And I'm measuring the period, and that's one of my other variables. So in this new formula, the two variables are t squared and 1 over k, instead of just t and k. What I notice is that if I relate that to y equals mx, y relates to t squared. So t squared would be on the y-axis. And x relates to 1 over k. So 1 over k would be plotted on the x-axis. And that means that the slope of my line would be equal to 4 pi squared times the mass that I put on the spring. So the units of my slope should be kilograms. So I'm going to plot t squared on the y-axis. I'm going to plot 1 over k on the x-axis. And my slope is going to be 4 pi squared times the mass. And my units will be in kilograms. And that will allow me to find the mass that I put on that spring experimentally. So how am I going to collect data in this lab? Well, it's not going to be that bad. It may be a little tedious at first. So when we go to this lab, first of all, you have kind of a quick introduction to how to use the data table, so make sure you watch it. And then you have an introduction to the video. So you're going to be looking at the relationship between K and T. And in this lab, you can pick different springs. You can set the mass and you can set the amplitude. And in this lab, you are going to click on the word change, and you're going to pick a mass and you're going to pick an amplitude. You're never going to change the amplitude or the mass again. All the springs will have the same mass and the same amplitude. And remember that in the end, if you picked a mass of, let's say, 200 grams, let's say that's the mass I'm going to use, that's really 0.2 kilograms. And let's say that I'm going to start with spring D. So if I do that and I press play, they're going to pull down on the mass, and then it's going to start oscillating. So you see it's oscillating pretty quickly. It's going to be really hard to measure one complete oscillation. So what you're going to do instead is you're going to measure the time it takes it to make lots of oscillations. So let me just define what an oscillation is. An oscillation is the time it takes it to go from the bottom position all the way down to the bottom position. So it starts at the bottom position, and then it goes up to the top and back down to the bottom position. That's really hard to do, and it's not statistically correct to just do it for one oscillation. What you want to do is you want to take your stopwatch, turn it on, set it where you can see it, take note of the time, 3.533, when it's at its first lowest point, and okay, so 3.500 is at its lowest point, and it goes 1 oscillation, 2 oscillations, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, so forth. So let's say that you counted it to have 16 oscillations at that time. Okay, so it started at 3.500 and ended at 6.5333. So here's what I'm going to do. This first column is going to be the total time, and it's going to be in seconds. And this is going to be the number of oscillations. Okay, so the total time it went from 3.500 to 6.533. So that would be 3.033, actually that would be, 3.033 seconds. We actually had 4 decimals there. And don't need to put the seconds in there. And the number of oscillations was 13. Okay, so that would be my number of oscillations. Okay, now I'm going to add another column over here. So I'm going to come over here and I'm going to add 1 to the right, and I'm going to tell it to calculate the period by taking the total time and dividing it by the number of oscillations. So that's time for 13 oscillations. I want to know the time for 1 oscillation. So if I take the total time and divide it by that, and that was not right, so let's clear that out. Total time divided by the number of oscillations, submit, and that tells me the total time for 1 oscillation. Okay, then I'm going to put in another column to the right, and that's going to be the spring constant. So this was spring D, and later on it's going to tell me that spring D had a spring constant of 22.87. 22.87, and the units are going to be newtons per meter. Okay, and the variable is A. The variable for period is seconds. The unit is seconds, and the variable is T. When you get ready to make new columns, you just click on the 3 dots, and you just say add a column to the right. If you wanted to create a T squared column, for example, you would just say change formula, and you would just say this column name, I would change the column name to period, and I would change this to spring constant. So when I come over here to do period squared, and I do change formula, I would just say period times period, like that. And I would call it period squared. And when I added my column for 1 over k, I would come over here and I would go insert to the right, and I would just say column formula, and I would say 1 divided by my spring constant. And I would say over here in my column name 1 over k. That would be fine. My units for period squared would be seconds squared. My variable would be t squared. My units for spring constant is newtons per meter, so this would be meter per newton, the inverse of that, and the variable would be 1 over k. So you're going to set up your chart like that. You're going to have to pick 7 to 8 springs to get data from. The more oscillations you measure, the better your average period will be, the better your data will be. And you're going to be exploring the effect that the spring constant has on period.